So Trenky is working with me on this topic, and so that's thank him too. So I was asked to come and give a tutorial on the evolution of our understanding of flux transfer events and the current status of that understanding, with an eye to the upcoming magnetopause crossing seasons of MMS. So here's a very vague, broad outline of what I'll talk about. Because it's a tutorial, I will talk a bit about some of the early work that was done on this topic to give some background, and then some of the results from the era post-2000 when we had observations from Cluster, Double Star, and Themis at Earth's magnetosphere, and also I'll touch on observations from Messenger too. So the work I'll present is mainly observational with some modelling elements as when dealing directly with the observations. And towards the end I'll kind of highlight a couple of examples where things could be done better with MMS. So, by way of background, I guess most people will be familiar with the open magnetosphere model that was put forward by Jim Dungy, who sadly died a few weeks ago. But this formed the basis of our understanding of how the dynamics, large-scale dynamics of the magnetosphere works, with magnetic reconnection occurring between the magnetic sheath or interplanetary field lines and terrestrial field lines, opening these field lines and adding into the tail, and then reconnection occurring on the night side as well. So this was put forward in 1961, but we had to wait a while for observations, direct observations of this reconnection process occurring at the magnetopause in order to drive this whole global convection. So I guess the expected signature of reconnection in this region was the presence of fast flows of the magnetosphere, which you get when reconnection occurs, as you transfer energy from the magnetic field into the plasma. And that was indeed seen in the 1970s. This is a summary of a couple of plots from a paper by Pashman et al. In Nature in 1979, showing a magnetopause crossing. The top panel shows the density of the plasma observed, which rises as you go from the magnetosphere into the magnetosheath. We have a flow. This is the ion flow here in the magnetosheath. But at the crossing, we saw faster flows, and that acceleration was shown to be consistent with what you'd expect from the reconnection process as it passed the Wallay test here. But actually, the first slightly more indirect evidence of reconnection occurring came in the form of flux transfer events. These were first reported by Russell and Elphick, or first discovered by Russell and Elphick. What they did is they plotted the magnetic field data from magnetopause crossings in a coordinate system they developed called a boundary normal coordinate system. This has two components that are in the plane of the magnetopause surface, and then the third component is normal to it. And so, if the magnetosphere is entirely closed, you would expect to see very little components of the magnetic field normal to the magnetopause. That would be a tangential response. But what they observed is the presence of these bipolar signatures at some of the magnetopause crossings, observed both in the magnetosheath and in the magnetosphere. And they were accompanied by enhancements in the magnetic field strength. Okay? So what their interpretation was that a burst of reconnection had happened somewhere, in this case south of the spacecraft, that gave rise to a bundle of open field lines. And so this was their sketch. It shows the magnetopause plane, the vertical arrows are kind of behind that plane, and then magnetospheric field lines are pointing upwards, and then you have downward pointing magnetosheath field lines in front. Reconnection has occurred off to the bottom and right of this plane. That set up two sets of open field lines, one set connected to the northern hemisphere. They move up, and you see that bundle here. They cross the spacecraft, and there'll be another set that are connected to the southern hemisphere, moving in the opposite direction. And so as this moves past the spacecraft, then you get a bipolar signature in the components that's pointing out normal to this surface, partly as a result of the fact that magnetosheath or magnetospheric flux drapes around the bundle that is formed, and partly because of the internal structure on that bundle. And so that was their interpretation, and that was the paper that introduced the idea of flux transfer events as bursty signatures, signatures of bursty reconnection at the magnetopause. A brief other footnote here is that actually similar signatures have been seen earlier, and we call flux erosion events. There's a slightly different interpretation, but they're still interpreted in terms of magnetic reconnection. But by plotting that data in this coordinate system, it's revealed that we're seeing the same thing with these bipolar signatures. So this is just a sketch showing the same thing, but in colour. I apologise to those of you who are colourblind. I was clued up to that when I created this figure. But we've got spheric field lines behind again, and the black, the sheath field lines are red, and this bundle is formed here. As it moves northwards, you get this positive, negative signature. If, on the other hand, you're seeing the partner that's in the other hemisphere and it moves southwards past the spacecraft, then the draping that you see, rather than being outward then inward, is inward then outward, and therefore you get a negative positive signature. So these are the top ones are known as standard polarity signatures, and the bottom ones reverse. And there's early statistical studies showed a separation, or rather the location was ordered by that polarity. So this shows statistical results of the location of flux transfer event signatures observed at the magnetopause projected into the YZ GSM plane. So we're looking towards the magnetosphere from the Sun. And the X's mark locations of standard polarity signatures, and the O's reverse ones. You see they're separated by a north-south divide, indicating that in general these events are formed kind of somewhere in the middle. And those that move north give rise to the standard signatures, and those that move south give rise to the reverse ones. Now, they're observed throughout the solar system. I will mainly be concentrating on Earth, but they have been observed at Jupiter and extensively now at Mercury, as I'll touch on later in the talk. Interestingly, we don't see these signatures in that form, these kind of bipolar signatures, clearly at Saturn, despite fairly extensive searches, even though we do see plasma signatures of reconnection, looking at rather more steady type of reconnection, although there are auroral observations that indicate that magnetopause reconnection at Saturn may be bursting. It's also been suggested quite recently that it may be occurring at the heliopause. In a sense, why shouldn't it? Because we know through the having seen the ribbon that the reconnection occurs at the heliopause, but it's suggested in this paper that in that J that perhaps the reason why Voyager didn't observe a significant change in the magnetic fields across the heliopause could be because the spacecraft had entered into an interstellar phase transfer event. And briefly as well, there are some laboratory experiments which kind of recreates these kind of structures. This is from a Tutorial just 2 years ago, showing the results of a real reconnection experiment, and this kind of loop of stuff here is the equivalent. And so that's kind of observed in the laboratory too. So I will mainly be concentrating on the signatures that are seen at the magnetopause, but it's important to note that flux transfer events as a process of bursty reconnection lead to a whole range of signatures, and actually a lot of good studies are done by combining observations from these different regions. So one example is the signatures that are observed in the cusp. So when you have steady magnetic reconnection at the magnetopause, then the injection of sheath plasma undergoes essentially dispersion effect, because on new Joachim field lines, if you're on a new Joachim field line down in the cusp, you're only able to see the fastest particles that have kind of travelled down, whereas if you're on a field line that has slightly undergone reconnections slightly earlier and therefore moved slightly further anti-tailward, then you'll observe kind of a more even mix, and so you only see the energetic stuff at the equator edge, and then you see gradually lower and lower energy particles move anti-sunward. But if you have pulses in the reconnection rate, i.e. flux transfer events, then you get discrete steps in the signatures that are seen here. And so that can be a very useful proxy for diagnosing the reconnection process at the magnetopause. And there's a range of other ionospheric signatures of flux transfer events, both in the auroral observations, and that's shown here. What you're seeing here is a time series of a whole series of stacks of a slice of the sky looking poleward. So at the bottom of this panel is a view looking southwards, and through to overhead, and then northward. And you can see these dark features which correspond to patches of aurora, because they are moving to the right and moving up as time goes by. They're moving poleward, and that is indicative of poleward moving auroral forms, which are the auroral signature of this process. And that's again due to the fact that when you have a pulse of reconnection, you set off a bunch of these field lines that move anti-sunward, so the auroral precipitation on those, the footprints are moving anti-sunward too, and so you get these poleward moving features. And similarly, you get poleward moving features in radar data. Here's just an example of a couple of plots from a paper by Faulkner in 98. Again, you have time on the x-axis, and the y-axis gives magnetic latitude. And you see these patches of red, which correspond to fast flows away from the radar, propagating, again moving up to the right, which indicates that they're moving to higher latitudes with time. And so these are referred to as either impulsed isotonic flows or poleward moving radar auroral forms, and they're all signatures of flux transfer events. So, going back to the spacecraft observations, and again some of the background, it was shown fairly on that they occur predominantly when the interplanetary magnetic field is southward, and that's including when you have a strong BY component. In fact, even when the IMF is slightly northward but strongly Y. That's shown in a histogram here that is showing a number of, a normalized number of flux transfer events for different clock angles, so that due north is at the top, due south at the bottom. And so that's consistent with the idea of burst reconnection, because that's favourable when the interplanetary field is southward. But those initial surveys were constrained to the pre-terminator region. So that's very much the day side. As soon as spacecraft surveys of flux transfer events started to sample the post-terminator region down on the flanks, they revealed the fact that actually on the flanks you get flux transfer events there for quite strongly northward IMF. Now you might expect, when the IMF is strongly northward, or you would expect the reconnection site to move to high latitude, and then you might expect to see signatures up there. These were observed down at the equator, but tailed with the terminator. And the IMF distribution of one of those surveys is shown here. So this top panel shows the events observed in the noon sector, and the colouring, the shading here is really purely to illustrate the symmetric part and the asymmetric part of the distribution. So the fact that you have the bars on the left-hand side, where this is BZ, negative to the left, positive to the right, you have higher bars on the left-hand side indicates that they're occurring predominantly for south IMF, but when you look at the post-terminator region, it's the other way around, you're getting a lot of events from north of IMF. Now, there were various ideas that were put forward at the time, but actually, I won't go into detail, but the cluster observations showed that actually you could track the motion of these events by making observations sequentially at 4 different spacecraft, and the cluster observations show that they are indeed moving equatorally, so they are formed at high latitude and move equatorally, and that can be understood in terms of the balancing forces on the flux rope at a high latitude reconnection site. So going back to these auroral signatures, I showed you the time series, but of course you can also look at the spatial pattern, either in the radar data at the left, or in auroral observations on the right. So these panels show the same view with the magnetic pole at the top, noon, NLT at the top, and so we have magnetic latitude and magnetic nodal time grid. And you see that the auroral feature that forms and moves poleward extends over several hours of local time. It's not just a very localized event. And similarly with the radar observation, these arrows show the velocity of these patches of radar scatter. And so that led to development of alternative models to explain these same signatures. First of all, this model based on multiple reconnection lines, put forward by Li and Fu. This is a view of the magnetopause from the sun. So we have some reconnection lines extending down like this. And between each pair of reconnection lines, you can get essentially field line kind of undergoing reconnection here, doubling back, undergoing reconnection again, doubling back, and this kind of repeats. And you end up with a flux rate forming that way, and similarly one down here between these two. A couple of years on, and a slight evolution of that idea was that perhaps the bursty nature of the reconnection process itself was sufficient to explain the bulge, the bipolar signature that you see, and you may only need to invoke a single reconnection line. So this sketch here is shown from a different perspective, now looking side on, and so the reconnection line maps in through here, going into the board, and as a result of an increase and then a decrease in the reconnection rate, there's been a bulge that is formed because of the heating of the plasma forces the magnetopause boundary layer to bulge out. So you get these kind of bulges of open field lines that propagate away from each other. And it's argued that although this is not a flux rope as such, unlike these and the Russell-Elphick picture, that these can give rise to the same signatures. And although I guess this is less commonly discussed, there's other ideas such as the structure that's seen arising as a result directly of the shear flow forming flow vortices, and then reconnection is triggered in there. And so rather than the structure being formed by reconnection, the structure is formed by this vortical flow, which then leads to reconnection. And so I'd also like to point out, if you're interested a bit more about the history of these models, in this relatively recent paper by Ferruggio et al., he talked about the motivation for developing these kind of bends here. So why is the difference between these important? Well, there's quite a fundamental mismatch between the estimates that are made of the significance of these events, depending on whether you look at spacecraft or ionospheric measurements. So if you take spacecraft measurements of these flux transfer event signatures, then the amount of flux that is estimated to be open to or contain one of these events equates to somewhere between 0.1 and 1% of the total open flux in the Earth's magnetosphere, in other words, the load flux. So each burst of reconnection would therefore only increase the load flux by 0.1 to 1%. If you then look at how frequently these events occur, there's a distribution, and you might often hear cited an 8-minute period for these events. That is the mean of the distribution, but notice it's quite skewed. There's a peak near 2 minutes, and this could even be kind of down to the resolution of how easy it is to identify these events. So they occur with quite a broad range of frequencies, but the mean is about 8 minutes. And so if you then work out how much flux might be opened per hour, then this ends up as being a relatively small figure compared with the refresh rate we know of the load in the polar cap. So that would imply that these events, whilst kind of interesting thing to look at, are kind of secondary to the large-scale steady-state process. But you can do that calculation another way around by looking at these kind of observations and work out, you can see the expansion of the polar cap resulting from the addition of open flux by each of these pulses, and by working out the area of that and knowing the magnetic field strength in the ionosphere, you can work out how much flux is added in each burst. And estimates using that method indicate that up to about 10% of the polar cap can be opened in any one go. And if that's the case, then this process of bursting reconnection could in fact be the dominant means of driving the Earth's magnetosphere. So why does this, another reason why this matters, I guess, is if we kind of look at Mercury, estimates of the significance there show that the role of flux transfer events is significantly more major there, actually. So not only is the amount of flux that's opened by each FTE larger, and this kind of shows a statistical estimate of that from a paper by Susie Imra last year. She has a series of histograms here where the duration of the event is shown, and this is just in seconds, so they are lasting between up to 8 seconds. The amplitude in relative to the background magnetic field is shown, and therefore she's worked out the flux content and has these events kind of transferring up to about 0.1 megavector. But that's when you then couple that with the fact that the repetition rate of these events at Mercury is faster than at Earth, perhaps with a repetition rate of 2 seconds, that indicates that actually the process of bursting reconnection at Mercury is very much likely to be the dominant driver of dynamics there. How does this kind of come about? Well, the reason for sketching this diagram was to try and, this is the panel I showed you before, but on the right-hand side here I've shown the other two mechanisms here, just to try and illustrate the differences. What people do is they work out the diameter of the structure that's moving past, therefore work out the area, and look at the axial magnetic field strength, and multiply that to get the flux content. And that's the correct thing to do if what is occurring is actually this Russell-Elphick flux tube. If you look at the structure on the right-hand side, you're not actually getting a flux tube at all. So even if you assume it is a flux tube, you're actually underestimating, because there's a lot of field lines over here that are opened by this reconnection line that are not going to be present in your calculation. And similarly, if this multiple X-line process is what's occurring, then you'll accurately be measuring the flux content that's opened in this flux rope here. But again, you're neglecting all of these field lines that are open to the burst of reconnection. So that can be the cause of the discrepancy between the ionospheric measurements, which are picking up all of this, and the spacecraft measurements, which are really only observing this. So in the rest of the talk, I'm going to concentrate on a handful of studies that have sought to try and distinguish between those mechanisms. And the first one I'm going to talk about is actually precedes the cluster era. It's a study using data from the AMTI satellite by Lockheed Hapgood, where it's a good paper I'd refer you to. They set out the differences between several of these mechanisms and tried to test some of them. And one of the things they did is they looked at the motion of the structure as it moved past the spacecraft. They found that was inconsistent with multiple X-line structure, but they then also modelled what they might expect to see in the spectrogram if either of the other two reconnection-based mechanisms were occurring. And so what they've shown here, the top panel, is as a function of time, the age of the open field line is being sampled. In other words, how long since reconnection occurred for that field line. And so the solid line, they trace out the case for the single X-line motion, where you're kind of intersecting an active X-line. And so as you cross onto the edge of the event, you're observing field lines that have only just recently undergone reconnection. As you go deeper and deeper, you're seeing older open field lines. And then as you come out the other side, again, you return and see field lines that have undergone reconnection more recently. Whereas with the Russell-Elphick model, they argue that actually it should be more the fossil, and therefore you suddenly enter onto field lines that have been open for a while, and then suddenly enter back onto field lines outside the event. And so here are two spectrograms that they modelled based on these different passages, and they compared it with the observed spectrogram. You see this kind of matches this top panel better. So they kind of, whilst they were not, they felt they couldn't be definite, they on balance favoured this single X-line mechanism over the other two. So then fast forwarding onto the cluster Themis era, a result that kind of conflicts with that last one to some extent is the fact that in recent years there have been several events and even statistical studies showing that we can observe converging jets on these structures. So and the significance of that is that it indicates that the structures are kind of within inside multiple X-lines, and therefore it's consistent with this multiple X-line model. So here we have time series of the magnetic field normal to the magnetic force of this panel here. The duration of the event is shown by the red bar, and we have electron spectrograms here. We see that the spacecraft was in the sheath throughout, but then at this time here observed an energization of the sheath population and also escaping magnetospheric plasma, indicating that it has moved on to open field lines. And at that time, we see different spacecraft in this study, bipolar signatures, negative and then positive, indicating that this is a flux transfer event that's moving southward. If you look either side of that, beforehand, you see flows. This is the north-south component of the ion velocity. Flows to the northward, followed by flows to the southward. So these are converging on the structure, and therefore indicate you've got X-lines either side. And so the interpretation in this study by Asgaris Tower was indeed that we have a structure that is embedded between multiple X-lines. And that's not unique. There are other studies showing similar things with different data sets. And there are also statistical studies nowadays, and it's found that these events where you are seeing actively converging jets indicating active multiple X-lines are relatively rare, perhaps because they indicate you only get these converging jets as the event is being formed, and then once it's formed it continues to move tailward, but we don't necessarily see the jets. Another useful tool for kind of studying these events that was developed actually before the cluster era, because it applied quite a lot to cluster and Themis data, is a process called Grashofanov reconstruction. This is started off as a single spacecraft technique. It's been extended to enhance it with multiple spacecraft, but therefore it should be something that can be applicable to LMS data. It will not matter that the separation of the spacecraft is going to be very small. What happens is if you make a pass through a structure in the magnetic field, such as a flux transfer event, then if the certain conditions are met, you can evaluate the magnetic field vector potential as you cut through and use that to infer what's occurring in the surrounding region. And you can trace out contours of the magnetic field perpendicular to the axes. One of the things you assume is that the structures here are essentially two-dimensional, so the changes in one axial direction are very small compared with the others, and therefore you can trace out the magnetic field in perpendicular to the axial direction, and then also infer the axial component. So this top panel shows contours of the magnetic field in the plane here, and then the color code gives the axial magnetic field strength coming out. The bottom panel shows the same, except the color code is now the thermal pressure inside the event. So you see quite a complex structure where the thermal pressure actually does not peak in the center of the event, it peaks around the edge of the event, and then the magnetic field pressure is what dominates in the core. So this is quite a useful technique for trying to infer what's occurring around these structures. And one thing that usually pops up from these is you usually end up with features that look like reconnection lines either side. So these reconstructions tend to lend themselves towards interpretations of multiple X-line reconnection. So a couple of other differences in brief between this kind of initial mechanism that's put forward by Russell Elkin and these longer reconnection line mechanisms. One of them is that by definition this is a fairly patchy structure, and whereas these structures extend quite a bit more in the east-west direction, that's why I think these were put forward when comparing with kind of ground-based observations. You can see extend over several hours of local time, but actually also now with spacecraft measurements, both from combining missions such as Cluster and Themis, and also taking Cluster at this very largest scale, we've been able to show that these do indeed extend further over the dawn-dusk direction than their north-south direction, so consistent with these kind of mechanisms on the right-hand side. And similarly, a difference that occurs between this and these two is that the orientation is different. So when you work, if you're able to infer what the axis is, then the axis should be, certainly for events we have a very high shear, very much more dawn-dusk for these structures, but north-south for these. And that's something that we have tried to examine, inferring the axes from not only minimum variance analysis of the draping of flux around here, and this shows some results from an event we studied, where the axes are plotted in the same plane as in this figure, so the fact that they're going left-right is more consistent with these kind of structures. When we tried to infer the axis from this branch of runoff technique, and we found a mixture of results, some of which were kind of consistent with the dawn-dusk axes that we got, and some that were very definitely not. The ones highlighted in dashed lines are highlighted as such either because there's a quality check within the branch of runoff technique to show how well the fit is done, and it either wasn't satisfied, or in some of these cases we had a very small number of data points within the event. So if the event only lasts 20 or so seconds, you're only going to get a few spacecraft spins within it, and then you're only going to get the plasma parameters you need for a handful of data points. If you have NMS data for this event, then we'd hopefully be able to get, if it were burst mode, plasma parameters at much greater resolution, and therefore the small number of data points would not have been a constraint. So another difference between this time the center multiple X-line mechanism and the ones on either side is that these on either side, by definition, produce one flux transfer event structure that is connected to the north and moves northward, and one that is connected to the south, because you're opening field lines, therefore you have field lines that are open connected to either hemisphere. The multiple X-line mechanism, though, is different in that the number of flux ropes it produces is determined by the number of X-lines minus 1. So if you only have 2 X-lines, you can produce a single flux transfer event. And that comes in useful because in a simulation by Jimmy Rader in 2006, he carried out global MHD scale runs and found that when he introduced dipole tilt, structures very much like multiple flux transfer events formed by multiple X lines formed and moved preferentially into the winter hemisphere. So you can see that there's a dipole tilt, it's northern hemisphere summer, and therefore one X line formed around about the equator and one at the stagnation point, I think it was, and the net result was that the structure is carried directly into the winter hemisphere. Now this bias isn't present in all simulations, but if there is such a bias observed in spacecraft measurements, it's really indicative of a mechanism that's capable of producing these structures individually rather than in pairs. Because if you have a pair, it's harder to explain how you might see it in one hemisphere and not the other. And this has been found to be the case. Korotova et al. In 2008 showed the results of of seasonal analysis for events observed by the interval spacecraft that crossed the magneticals at high latitudes in the northern and southern hemisphere, kind of similar to cluster, but with a different orbital phase. So it was actually crossing the near-noon magneticals around about June, July. And so here is showing the magneticals crossings from around solstice in the northern hemisphere and in the southern hemisphere. So this is the YZ descent plane event. The pluses indicate the events, the magneticals crossings on which no flux transfer event signatures were seen, and the diamonds indicate the crossings on which there were FT signatures seen. And you see the signatures were all observed in the southern hemisphere, which is the winter hemisphere for this event. That's been verified as well with cluster data. As I mentioned, the orbital biases are different, and in fact it was found that you really do need to take into account the seasonal effect in order to try and understand the distribution of these events. Now, a slight puzzle that arises from this Leo-Fu multiple X-line mechanism, if that is indeed occurring, is that, as they noted in their paper, there's quite a range of different topologies that can be observed. The reason for proposing this was to try and explain the transfer of flux into the magnetosphere, and if you have multiple X lines here, then the usual case that's considered is where you have a field line that will undergo reconnection at this X line and then doubles back and so on, and then ends up connected to a magnetospheric field line. So this is sheath, and then this is magnetosphere. So you are transferring flux into the tail. But as they noted in their paper, the actual connections that occur just depend on the relative length of these reconnection lines. So if the reconnection line undergoes here, if reconnection continues as I mentioned before, the field line undergoes reconnection here, but does not here. It goes on being connected from the sheath into the sheath again. And if you have a slightly different region along which reconnection can occur, then you end up with connections from the magnetosphere back into the magnetosphere. So the question then became, why don't you see those kind of things? Well, it looks like we do. This paper from Pu et al. In 2013 analysed the flux transfer event, and at different phases in the crossing of that event, they felt they had 4 different types of field topology. Open field lines that were connected to the southern hemisphere magnetosphere, and this is indicated by the pitch angle against energy, so the spectrogram is kind of on this side of it. And the fact that we see this energetic magnetospheric population coming along parallel to the field, but nothing coming anti-parallel, is consistent with the connection to the southern hemisphere. Opposite to that, we see the connection to the northern hemisphere, but with some, in both of these cases, we've come across sheath plasma entering as well, so in the case of the field line is open. But then we have some regions where you have energetic magnetospheric particles at all pitch angles, suggesting that you're on but even though you have as well trapped some sheath plasma that's energized, indicating you're on field lines that are closed and connected at both ends to the magnetosphere. And similarly, cases where you have energized sheath populations at small pitch angles and nothing much in the way of magnetospheric plasma, indicating that we're on kind of loops that are closed into the magnetosheath. And similar kind of explanation was used in this paper that's in press on the JGL website, which does quite a thorough study of a couple of flux transfer events observed in the sheath. And again, we see, they noted that there's quite a lot of different structure, a lot of interfaces here, a mixture of tangential and rotational discontinuities in this structure that aren't necessarily kind of accounted for in the simple kind of sketches that have been done in the past. But by looking at the variations in the pitch angle and the plasma populations that we go through, they conclude that at different times there are different numbers of feet of the field line on the connected to Earth. So it starts off with the magnetosheath, and therefore the field line is not connected to Earth at either end. But then you enter into the event, and there's a region where there are bidirectional heated sheath plasma, suggesting that you're, because we're in the sheath, this can't be explained by mirroring as such. So it does suggest that the field lines here are connected to the magnetosphere at both ends, and then kind of moving through a section where you just got a more conventional single connection, and then back out into the sheath again. So they kind of came up with this kind of sketch to show the structure. Partly the green field line is draping but then the red and the blue, the red is the field lines that simply connect the magnetosphere at one end, as you might have expect from the sketches before. The blue is a field line where it looks like it kind of loops around, so you have connection to the magnetosphere at both ends. So that can only really be explained by this multiple X-line model. Another interesting topic is the some of the crater signatures, where I mentioned that the magnetic field strength in the centre of these events typically peaks, but in fact you also have events where you get a dip in the centre and then crater FT signatures. They've been studied quite extensively, and one suggestion has kind of been ongoing, but it's been really studied much more in depth by this recent Verruga paper, is that the reason for this structure is that as you kind of cross the edge here, you are actually intersecting the separatrix, and so you're observing field lines that are connected to the X-line, and this was shown by the fact that in the region around here that they label as region 2, there is a lot of electric field activity and electron signatures that are consistent with encountering the separatrix. And they suggested that a lot of progress in understanding reconnection can be undergone by studying these FTEs, particularly crater signatures, particularly with MMS data. And the reason for that is shown in this study by Ali Bassani et al., which uses data from cluster, which normally you can only get a pitch angle distribution every 4 seconds due to the spin. But there are certain, if you have a lucky event where the magnetic field is aligned quite close to the spacecraft spin axis, then then if you have 3D distributions, as you sweep through that distribution, all of the time you're picking up most pitch angles. And so therefore they reported kind of pitch angle distributions at sub-spin resolution. So this is kind of quite typical of what you'll be able to get with NMS. And they noted that although they recovered the structures that were reported by Verruga et al., there was a lot more substructure in there, with lots of multiple layers, and some very clear boundaries identified that would just be aliased with spin resolution data, because these would cross so quickly. So I think there's a lot of structure here to try and understand with NMS. And finally, just as a brief aside, I mentioned in one of the earlier slides that there are also models based on vortical flows then reducing reconnection. I think that seems to be discussed less in the context of observational studies, but it is discussed in some MHD simulations, such as this one reported by Tutorial1 and Tutorial1. So what you're seeing here is the XZ plane, and what they do is they color code the field lines according to their topology. So we have closed field lines connected to the magnetosphere at both ends, the sheath or sort of window here where the field lines are declaratory, and the green and white mark regions of field lines that are connected to the northern and southern hemisphere respectively. And in their simulations they get a vortical flow that arises, and therefore the structure forms and then reconnection follows afterwards. So they can interpret the reconnection as a consequence of the FTE and not the cause of it. The other thing they do here is they consider much more the process in terms of fully three-dimensional reconnection. So a lot of the discussion I've given so far is kind of thinking in terms of what's called 2.5-dimensional reconnection, where you do the 2D sketch and then just extend it into the third dimension. Whereas in context of solar physics, particularly, reconnection is very much considered as an intrinsically three-dimensional process, and therefore there's kind of a bit of a difference often in terms of the terminology and understanding between the two fields. And so I think that, although there are some spacecraft studies that try to consider the events in terms of 3D concepts, I think there's quite a bit more that can be done to try and link these fully 3D concepts with the conceptual models we have for these structures. So to summarise, there's a handful of different mechanisms that put forward for these, and there are different studies that seem to side with different mechanisms. Although I know that this original Russell picture is still the favoured model of choice for some people to interpret their events in. In terms of model studies that then try and compare with predictions that try to distinguish between them, they tend to side with one of these two, I would say, in general. But I think there's still a lot of work to be done to try to understand which of these occurs when and why, and also how much a role this kind of vortical effect has. So to summarise, flux transfer events are potentially the major driver for magnetospheric dynamics at Earth. They certainly are at Mercury, though we have got this order of magnitude discrepancy between spacecraft and atmospheric estimates of their significance. I think we've made a lot of progress in the cluster and Themis era, but there still is debate about the mechanism that causes the formation of these events, and there's work to be done on reconciling some different observations and also building a 3D connection picture. And I think that a couple of the studies I showed where either the lack of number of data points across the event or the use of the subspin resolution data from cluster, which is only available under very favourable conditions, show the potential for what we'll be able to do with MMS. Thank you.